All right, welcome to the video Limits at Infinity, also known as end behavior. All right, we're going to explore limits as the x values go to either positive or negative infinity. So far, we've been dealing with just as x approaches some c value, some x on the real number line. But notice that we're going to be exploring limit questions where x either approaches the positive or the negative infinity. And if you scan down at all the problems on the front of the worksheet, you're going to see that these are examples of limits at infinity. All right, so here's the calculus notation that's asking you about the end behavior of this graph. Well, you might remember that that graph, that cube, let me change colors here. Okay, that cube graph has end behavior that looks something like this. This is just a rough sketch to answer the end behavior question. Okay, so if you think about this graph modeling this equation right here, okay, if you were asked as x approaches infinity, goes this way, what are the y's approaching? In your past math classes, you would have used words that said just that. As x approaches infinity, the y's are going to, you can look at a graph and go, hey, negative infinity. Okay, and the other question might be paying attention to the limit statement here. As x approaches negative infinity, no, I'm going to X out of that. Sorry about that. As x approaches negative infinity, the y's are going to positive infinity. The only thing is that you have to remember what the basic shape of this graph looks like as determined by this leading term. So this first term, or not just the first term, but the term with the highest exponent determines what the graph looks like. And from the graph, you can respond to these questions right here. I don't know where that went. Okay, now, if you can't even remember what the graph looks like based on this leading term right here, that's okay. In calculus, there's an easier way without having to look at the graph to find these limit answers. So you can just watch. Hang on, give me a second. It's been a while. There's the tools. I'm going to change colors. So you guys are just watching. Okay, so if you want to remember what the graph looks like, wonderful. Otherwise, here's another option. In calculus, if we're finding the limit of this function, all we have to do is capture the leading term. And it doesn't mean that it's the term that starts the whole problem. It's just the term with the highest exponent. So in this case, it'd be this term. Okay, if I find the limit of the leading term, oh goodness, okay, I'm just going to capture this first term right here, and everywhere I see x in it, which is just right here, I'm going to replace it with infinity. So -3, oh, no, okay, times infinity cubed. Well, infinity cubed is just infinity times -3 is negative infinity. So does that match the answer we found by remembering what the graph looked like? Sure, it does. Yeah, I don't know where these things are going to. I'm just going to go with it. All right, and then you can see likewise in this limit statement right here too, if I were to change this to negative infinity and plug in negative infinity into the leading term and do the computations, well, negative infinity cubed would still be negative infinity, but times a negative number would give me a positive infinity. So prior to calculus, prior to limit statements, you would have had to remember what the graph looks like to discuss the end behavior. But in calculus with limit statements, capture the model or the leading term and insert infinity there, and you're good to go. There's my equation 2. All right, hopefully this isn't in the way. I'm going to leave that there. It seems to do better when that's there. Okay, let's look at example 2. Okay, kind of the same thing here. From your past background in math, you know with the even function with a negative coefficient, this is just the general shape of that graph. Both of these answers will be negative infinity here, because whether you go to positive or negative infinity, the y values are going to negative infinity. Okay, well, if you don't want to remember the graph, do what I just said with calculus and infinity limits. Go to the leading term. Again, it's not just because it's the term that comes first, it's the term with the highest exponent. Okay, take infinity and plug it in for x. So negative 2 times infinity to the fourth. Well, infinity to the fourth is just going to be infinity times a negative. The result is going to be negative infinity, which matches up with the picture that we just see. All right, plug in negative infinity to the leading term. Well, negative infinity to the fourth power is still going to be positive infinity, but you have to go back and multiply by negative. So that is also going to be negative infinity, which is what we thought from the graph. All right, so polynomial functions just mean that you have an equation with x's with integer exponents. That's a polynomial function. They're well behaved. There's no breaks in them. They're continuous. The limit exists everywhere. The functional value equals the limit. Just trying to review some things too. All right, let's look at rational functions because that's where we need to spend a little more time. All right, so with rational functions, okay, they're a little more complicated. Okay, but we're going to take the same approach as we did in the last few problems up here as far as the calculus approach. Okay, so we have this function and we're interested in the end behavior as x goes to infinity and x goes to negative infinity. Okay, well, in the past, what you've done is you've had to compare the degrees of the exponents in both the numerator and denominator. And it's kind of hard for me to scroll down, but I want you to look at the bottom of your worksheet. Okay, you'll see where it says asymptotic behavior of rational functions. And there are 3 cases there. So if you're looking at it, case 1 says the degree of p is less than the degree of h. Okay, don't get caught up in that. That just means is the degree of the numerator, the highest exponent in the numerator, smaller than the highest exponent in the denominator. And if so, y equals 0 is the end behavior asymptote. And that's what you learned from Algebra 2 and Pre-Cal, that when you compare the exponents, if it's smaller on top, okay, there's an asymptote, a horizontal asymptote of y equals 0. Okay, so think about 1 can be replaced with x to the 0 power, because that's just 1. Think about comparing the 0 exponent with the 2 exponent. Well, according to what we've learned in the past, when you compare those exponents, it's case 1, and y equals 0 is going to be your end behavior asymptote or a horizontal asymptote. So both of these limits at the extreme left and right are going to go to 0. You can produce a graph if you want. That's one I can do without a calculator, just because I know the parent function. Okay, and this graph has shifted left 5, and it looks something like this. So you can easily see from the graph that the y values are going to 0, both at positive and negative infinity. All right, if you're looking at the bottom again of your worksheet, you guys can see that. Let me kind of get down there. It seems to take a while. Okay, if you look down there, there we go. Okay, so we've been lingering right here in the problem we just did, and what you learned in Algebra 2 and Pre-Cal was that there was a horizontal asymptote of y equals 0. Well, here's the calculus notation that supports that you have a horizontal asymptote at y equals 0. All right, well, what happens if the degree of the numerator is this polynomial, is less than, or is not less than the degree of the exponent of the denominator, the h? Well, these are the other 2 cases. Okay, so let's look at the other examples that we have. All right, so for example 2, what I'm doing is I'm taking an algebraic pre-cal approach here, and then we're going to come back and say this is how we look at it from the calculus standpoint, like I did back up at the top. Okay, look at number 2. For this rational function, look at the degrees of the numerator and denominator. They're equal. I'm not going to try and scroll down again because it's acting funny. If the degrees are the same, I'm down in case 2. And in case 2, it says that y equals k is the end behavior asymptote, where k is the ratio of coefficients of the lead terms. So what you would have done in Algebra 2 pre-cal is you would have looked at the coefficients 3 and -5, and you would have said there's a horizontal asymptote at -3/5. So both of these limit questions become -3/5. Okay, look at example 3. Okay, so I've got the limit statement all in the function here. I put it together, and as you can see, these two right here deal with the same function. Just one's going to infinity and one's going to negative infinity, and then likewise here. Okay, so let's look at this case right here. I would have to FOIL the denominator, distribute, expand, multiply, and the highest degree down here I'll have to do that later. Okay, is I want to just consider this product being an x cubed. All right, well, let's compare the degrees now. Okay, well, the highest degree is going to be 4 in the numerator, and the highest degree is going to be the 3, no matter how you multiply it. So look down at the bottom, and you can see that when the degree of the numerator, p, is greater than the degree of the denominator, or in case 3, okay, we have a slant asymptote. So you might have answered back in Algebra 2 and pre-cal, whatever, you might have answered that there's none, meaning no horizontal asymptote, because the end behavior asymptote is on a slant. And that's how you would have left it. Well, notice that our answer needs to either be plus or minus infinity for the problems where the degree of the numerator, like number 4, is greater than the degree of the denominator. So all these answers for these 4 problems are going to either be the positive infinity or negative infinity. And I'm going to show you how to find them pretty easily. Okay, so I'm going to come back up here, and I'm going to show you the calculus approach. All right, so we're going to get these same answers right here, but we're going to use the calculus approach. So going forward in the future, if you have a limit at infinity, this is what you're going to do. The limit as x approaches infinity. Capture the end behavior model, like we did back up here for the polynomials where we just chose the first terms. We're going to do the same thing here. We're going to choose the leading term. I said the first term, should be the leading term. I'm going to choose the leading term of the numerator and the leading term of the denominator, and then we'll go from there. So for this problem, it's just going to be 1. It can be changed to x to the 0 to compare exponents, but I'm just going to keep the 1. Down here, if I were to expand, okay, multiply it out, I would get an x squared term as the leading term. Once you capture the model, that means the leading term on top and bottom, simplify this expression. After you simplify it, plug in infinity, and let's see what happens. So now I'm going to plug in infinity. Well, 1 over infinity squared is just going to be infinity. What is 1 over infinity squared? Well, the value of that fraction is going to go to 0, hence I would know that my answer should be 0. Which matches up with what I found here by comparing the degrees of the exponent and doing all that memorizing. All right, so let's do this one. What's the limit as x approaches infinity? We capture the model. The model is the leading term of numerator and denominator, just like it's the leading term of the polynomial. Plug in, that should be a negative infinity, sorry. 1 over negative infinity squared. Well, that's still just infinity, and 1 divided by infinity is going to be 0. All right, so the easy way to find end behavior through calculus or limit notation is to capture the model, reduce it, and plug in your infinity to see what your answer is. So let's see if we can end up with these same results by doing the calculus technique. So from this point forward, if I'm finding these, this is what I would show. Based on the equation I'm working with, I would capture the model, which I think that was 3x cubed over negative 5x cubed. Don't plug in infinity until you simplify. Watch my equals. Keep the limit, because in this step I'm doing algebra of simplifying. Those are going to cancel, and I'm just going to be left with negative 3/5. Well, there's no x to plug in infinity, so guess what? This is the basic limit idea, that property, so my answer is just negative 3/5. So no memorizing exponents and how they compare, just simply capture the model, reduce, plug in your infinity, and go with the result. So let's look at this one. As x approaches negative infinity. Same model. We call this model, what it does at its ends is exactly what this graph does at its ends. So that's why it's legal mathematically to use the model. All right, we're going to cancel, plug in negative infinity. Okay, but here I'm just going to go straight to negative 3/5. I'm not going to rewrite it. All right, let's see how we're doing on time here. Oh, good. All right, let's look at example 3 and 4 before I messed it all up. Okay, I'm presented with this problem. I need to find the limit. Okay, I'm dealing with end behavior because of the infinity. Whatever this graph is doing as it comes on and leaves the screen, okay, would be the same as the model. The model for this function, what it looks like, capture the leading term on top. Now, I'm going to have to do a little work on the bottom. To capture the leading term in the denominator, I would have to expand and get x cubed. Don't plug in infinity until the model has been simplified. So bring the limit over, simplify. So that means when I simplify, I'm going to have 3x. Now plug in infinity, and 3 times infinity just results in infinity. This is the progression of the work for this problem that results in an infinity answer. So as x takes on large values, the y's of this graph are going up to positive infinity. Okay, so let's do the same thing here. All right, I need to tackle this problem. This is end behavior. Let me look at the model. The function that looks like it at its ends. Well, that's 3x to the 4th divided by x cubed. I know I need to simplify those, divide out, leaving 1 on top. I'm going to clean it up and rewrite it, but I'm going to keep the limit statement. So I end up with 3x. I'm going to plug in negative infinity, multiply it by 3, and get a negative infinity output. For those of you guys that are curious, I would type that into y1, and I would see that the graph leaves the screen up, going up on the right side. Okay, and the graph comes on the screen from down below on the left side. All right, so let's look at another example with 4. All right, let's find this limit. I want to know the ends. It's end behavior because I'm going to infinity. The model would have us take 5x to the 6th. It has the most impact on the numerator, so it should be part of the model, over 2x squared. And watch out, because sometimes it's just not the upfront term here. It could have been rearranged. Don't plug in infinity just yet. Simplify first. If you plug in infinity too early, you get infinity over infinity, which is another form of indeterminate. All right, so I've got 5 halves. 2 will divide out of 6, leaving 4 of them. 5x to the 4th. Plug in infinity, take it to the 4th power, which is positive infinity, times another positive number. The result is a positive output. So I guess you're seeing that when the degree of the numerator is larger than the degree of the denominator, my answer is either a positive or negative infinity. If my degree is smaller than or equal to, okay, the denominator's degree, then it's going to be a number, either 0 or the ratio of coefficients here. Oh, sorry, again, that should be negative infinity. Plug in negative infinity, take it to the 4th power. That makes it positive. Positive infinity times 5 halves is positive infinity. So when you're looking at the idea of end behavior, capture the model, reduce it, insert the appropriate infinity, and then end up with whatever result you might have, a number, 0, or another constant, or either a positive or negative infinity. But no more having to memorize the degrees of the numerator and denominator to figure out what the answers are. All right, and this is just for your reminder down here about vertical asymptotes and where they occur. Okay, where the denominator is made 0, and wholes. Okay, and that is a typo. That should be numeric. Okay, wholes occur where when you plug in numbers to the equation, you get 0 over 0. Okay, possible wholes. There could be jumps there too, but that's just a way to describe a removable discontinuity. If it does occur, it's going to occur where it's 0 over 0. And then just a reminder of the comparison down here. The connections and the comparisons of the rules you learned in the past about finding end behavior asymptotes from the past when you compare the degrees, and then also the calculus look at end behavior using notation. All right, so hopefully you have a good idea of how to find limits at infinity when you're dealing with polynomial and or rational functions.